And now in this lecture we find out the radius of the small circle. In the drawing we have a quarter circle, AOB is a quarter circle. Note that side OB of the quarter circle equals to 16 units left. That is to say the radius of the quarter circle equals to 16 units actually. AU is also the radius of the quarter circle, that is equals to 16 units left. So write it down. So we note that the radius of the quarter circle equals to 16 units in its length. In addition, inside this quarter circle AOB we have this semicircle and this small circle. And our mission is to find out the radius of this small circle, or to find out the value of R, that is the radius of this small circle. So first of all, we define the relevant points to this question with letters. We define the center of this semicircle, this point, as point P. Likewise, we define the center of this small circle, this point, as point Q. We define the point of tendency of tangent OB with this small circle, this point, as point M. And we define the point of tendency of this small circle, or the touching point of this small circle with this semicircle, this point is point S. And finally, we define the touching point of the big quarter circle with this small circle, this point is point T. So we know that AOB is a quarter circle, therefore angle AOB must be equal to 90 degrees in its size. Because AOB is a quarter circle. Here we can implement rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have this circle and we have tangent AB that is tangent to this circle here at point M. This point M, and we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius QM that is equal to R. The radius QM is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say, from point Q, that is the center of this small circle, we will draw perpendicular on AO. Again, from point Q, we will draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. By doing this construction, we can dedicate quadrilateral QH OM. Inside quadrilateral QH OM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral QHOM we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this right angle if not a square. So we write this quadrilateral QHOM as right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side HO, but QM equals to R. Therefore HO must be also equal to R. We know that AO is the radius of the quarter circle, and it is equal to 16 units in its length. But AO is not only the radius of the quarter circle, but it is also the diameter of this semicircle. So we know that AO is the diameter of the semicircle. So the diameter of the semicircle equals to 16 units in its length. Therefore, the radius of this semicircle must be equal to half of it. It must be equal to 16 over 2, that is 8. So the radius AP of the semicircle equals to 8 units in its length. And the radius PO of the semicircle also equals to 8 units in its length. So what is the length of the small line 7 PH? PH equals to PO minus HO. Again, PH equals to PO minus HO. So write it down. PH equals to PO minus HO. So PH equals to PO. PO is 8, it is the radius of the semicircle. This is equal to 8 units in its length, point also HO. We just have to find out that HO equals to R. So in total, PH equals to 8 1/3. PH equals to 8 1/3. So write it down here. This small line side PH equals to 8 minus R units in its length. Okay. So here, this semicircle touches this small circle at point S. That is to say, those two circles have an external line between them at point S. And whenever you have two circles that have an external line between them, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing you have two circles. Those two circles touch each other at this point, point P. That is to say, those two circles have an external line between them at point P. The center of this circle is here at point O. The center of this circle is here at point M. So according to this rule 10, the straight line that connects the centers together is of course the straight line OM. The straight line OM must pass through point P. Again, the straight line OM must pass through point P. Or OPM is one straight line. Again, OPM is one straight line. Okay. So you can actually implement rule 10 in our drawing. Why? Because in our drawing, as I mentioned before, this small circle has an external line with this semicircle. That is to say, those two circles touch each other externally at point S. And therefore we can implement here rule 10. The center of this semicircle is here at point P. The center of this small circle is here at point Q. And the straight line that connects their centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point S. again the straight line PQ must pass through point S, or PSQ is one straight line, and PSQ is one straight line. So we connect points P and Q together by straight line, and the straight line PQ will pass through point S. You see here, the straight line PQ passes through point S, according to rule 10. But what is exactly the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and ends at point S, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore PS is the radius of this semicircle, that is equal to 8 units in its length, according to what we already found out. What is the definition of line segment QS? Line segment QS starts from point Q, that is the center of the small circle, and ends at point S, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore QS is the radius of this small circle, that is equal to R. And because of the fact that PSQ is one straight line, according to rule 10, it means that PQ is also a straight line, and PQ will be equal to PS plus SQ. Again, PQ equals to PS plus SQ because PSQ is one straight line. So write it down. PQ equals to PS plus SQ. So PQ equals to PS. PS is 8 plus SQ. SQ is R. So in total, PQ equals to 8 plus R. Okay, PQ equals to 8 plus R. In the next step, I'll copy the right triangle PHQ in the new page, and we'll implement the Pythagoras theorem on this right triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evolution for Pythagoras theorem. We just right now found out that the hypotenuse PQ equals to 8 plus R with the green triangle. We already found out that side PH of the green triangle equals to 8 minus R. And this side HQ is the missing side, so we leave it as it is. So actually, this is the right triangle PHQ is the coordinate from the original drawing, according to the Pythagoras theorem. In this right triangle PHQ, PQ squared, that is the square of the hypotenuse, must be equal to PH squared plus HQ squared. PH is 8 plus R, therefore PQ is 8 plus R. Yeah, this is the hypotenuse PQ is 8 plus R, therefore the square of the hypotenuse is 8 plus R squared, and it must be equal to PH squared. PH is 8 minus R, therefore PH squared is 8 minus R squared plus HQ squared. HQ is the missing side, so we leave it as it is. So here we'll open the brackets on both sides of this equation 1, and again that according to this equation 1, 8 plus r squared equals to 8 squared, that is 64, plus r squared, plus 2 times 8, that is 16 times r, so this is plus 16r, equals to 8 times r squared. 8 times r squared equals to 8 squared, that is 64, plus r squared, plus 2 times r, that is 116 times r, so it is 116r, plus hq squared. So here we have 64 on both sides of this equation 1, so 64 will get cancelled. And we have also r squared on both sides of this equation 1, so r squared also will get cancelled. So what is left on this equation 1 after we cancel those two expressions? What is left is that in this side of equation 1 we left only with 16r, on the other side of equation 1 we left with minus 16r plus hq squared. So here we will add 16r to this equation 1, and we get that here 16r plus 16r plus 16r is 32r, so 32r equals to hq squared. So here we substitute 32 by 2 times 16, and again according to this equation 1, 16 times 2 times r equals to hq squared. So here we take a root out of this equation 1, and we get that according to this equation 1, hq equals to the square root of 16 is 4, so it is 4 times square root of 2r. Inside the root we left only with 2r, so we actually found out that hq equals to 4 times square root of 2r. So actually this is side hq, this is equals to 4 times square root of 2r. But we already found out that for the other hq MO is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQ MO, side HQ must be equal to the opposite side MO. But HQ equals to 4 times square root of 2r, therefore MO must be also equal to 4 times square root of 2r. So let it know, MO equals to 4 times square root of 2r. So here we have the small circle touches the big quarter circle at point T. That is to say, those two circles have an internal length between them at point T. They are touching each other internally at point T. And whenever you have internal length between two circles, you can implement rule 9. I'll repeat quickly rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching points. So here we have, this is the big circle, the center of this big circle is 0.0. We have this small circle, the center of this small circle is 0.0, at point M. And the straight line that connects their centers together is of course the straight line OM. According to this rule 9, the straight line OM must pass from point P. Again, the straight line OM must pass from point P, or OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. The small circle have internal match with the big quarter circle. That is to say, those two circles touch each other internally at point T. Therefore, we can implement here rule 9. According to rule 9, we know that the center of this quarter circle is here at point O. The center of this small circle is here at point Q. So the straight line that connects their centers together is the straight line OQ. And according to rule 9, the straight line OQ must pass through point T. Again, the straight line OQ must pass through point T. This is the touching point. Or OQT is one straight line. Again, OQT is one straight line, according to rule 9. So this is the straight line OQT. If OQT is one straight line, it means that OT is also one straight line. OT is a straight line, but what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and that's at point T, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of the quarter circle, that is equal to 16 units now. So write it down, OT equals to 16. What is the definition of line 7 QT? Line 7 QT starts from point Q, that is the center of this small circle, and that's at point T, that is the point on the small circle itself. So this is exactly the definition of radius. Therefore, QT is the radius of this small circle, that is equal to R. And because of the fact that according to rule 9 OQT is one straight line, it means that OQ must be equal to OT minus QT. Again, OQ must be equal to OT minus QT. So I write it down. According to rule 9, OQ must be equal to OT minus QT. So OQ, the length of this line segment OQ must be equal to OT. OT is 16 minus QT. We just said now found out that QT equals to R. So in total, OQ equals to 16 minus R. This line segment OQ equals to 16 minus R units in its length. In the next step, I'll copy the right blue triangle OQM in a new page, and we'll implement the Pythagoras theorem on this right blue triangle OQM. Here by PT is a relation for Pythagoras theorem. We have already found out that side OM of the blue triangle equals to 4 times square root of 2R. The hypotenuse QO equals to 16 minus R. And QM, side QM of the blue triangle equals to R. It is the radius of the small circle that is equals to R. So actually, this is the right triangle OQM that are going from the original domain according to the Pythagoras theorem. In this right triangle OQM, OQ squared, that is the square of the hypotenuse, equals to QM squared plus OM squared. The hypotenuse OQ is 16 minus R, therefore OQ squared is 16 minus R squared, and it is equals to QM squared. QM is R, therefore QM squared is R squared plus OM squared. OM equals to 4 times square root of 2R, therefore OM squared is 4 times square root of 2R squared. So according to equation 2, we can find out that 16 minus r squared equals to r squared plus 4 times square root of 2r squared. Here we open the brackets on this, both sides of this equation and equation 2. And again, that according to this equation 2, 16 minus r squared equals to 16 squared, that is 256, plus r squared minus 2 times 16, that is minus 32 times r. So it is minus 32r equals to r squared plus 4 times square root of 2r squared equals to 4 squared, that is 16. And square root of 2r squared equals to 2r, because the power square cancels the root and you left only with 2r. So here we have r squared on both sides of this equation 2. So r squared gets cancelled. After cancelled r squared, in this side of this equation 2, we left only with 256 minus 32r equals 2. In the other side of this equation 2, we left only with 16 times 2r is 32r. So according to equation 2, we can find out that 256 minus 32r equals to 32r. Here we add 32r to this equation 2, and we get that according to this equation 2, 256 equals to 32r plus 32r is 64r. So according to equation 2, we can find out that 256 equals to 64r. Here we divide this equation 2 by 64, and finally we get that r equals to 256 over 64 is 4. So r equals to 4 units in its length. And again, the answer to the question is that the radius of this small circle r equals to 4 units in its length. So in the next step, I'll summarize the lecture. In this lecture, we found out the radius of this small circle. We found out the value of r. In the domain, we have a quarter circle. AOB is a quarter circle. We know that side OB equals to 16. That is to say, actually, the radius of the quarter circle, the radius AO, that is equal to radius OB, this is actually the radius of the quarter circle, equals to 16 units in its length. That is to say, AO, that is also the radius of the quarter circle, equals to 16 units in its length. In addition, inside this quarter circle AOB, we have this semicircle and this small circle. Repeat again that our mission is to find out the radius of this small circle or the value of r. In the first step, we defined the relevant questions, the relevant points of this question with letters. We defined the center of this semicircle, this point as point P. We defined the center of this small circle, this point as point Q. We define the point of tendency or tangent OB with this small circle, this point is point M. We define the tangent point of this small circle with this semicircle, this point is point S. And finally, we define the tangent point of the small circle with the big quarter circle, this point is point T. We know that AOB is a quarter circle, therefore angle AOB must be equal to 90 degrees in size. Okay. In the next step, we did the construction. That is to say, from point Q, we do perpendicular on AO. Again, from point Q, we do perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. By doing this construction, we can do quadrilateral HQMO. Inside this quadrilateral HQMO, we have 1, 2, 3 alternatives. The sum of 3 alternatives is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral HQMO, we have 4 angles, and according to rule 6, any quadrilateral that has 4 angles must be at least a rectangle in front of square. So in order to this quadrilateral HQMO, it's a rectangle because it has 4 rectangles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle HQMO, side QA must be equal to the opposite side AQ. Again, side QA must be equal to the opposite side AO. But QA equals to R, therefore AO must be also equal to R. Actually, the small circle touches the semicircle at point S. That is to say, they have an external arch between them at point S. And whenever an external arch between two circles, you can implement rule 10. I'll keep quickly on rule 10. According to rule 10, if two circles touch each other externally, then the side line that connects their centers together passes for their touching point. So in the drawing we have two circles. Those two circles touch each other externally at point P. So they have an external arch between them at point P. The center of this circle is at point O. The center of this circle is at point M. And the side line that connects their centers together is of course the side line OM. So this side line OM, according to this rule 10, must pass for point P, that is their touching point. Again, the side line OM must pass for point P, that is their touching point. Or OPM is one side line. Again, OPM is one side line. So we can implement rule 10 in our drawing. Why? Because in our drawing we have this semicircle touches this small circle at point S, so they have an external arch between them at point S. The center of this semicircle is here at point P. The center of this small circle is here at point Q. And the side line that connects the centers together is the side line PQ. So according to rule 10, the side line PQ must pass for point S. Again, the side line PQ must pass for point S, that is the touching point. Or PSQ is one side line. Again, PSQ is one side line according to rule 10. But what is the definition of line 7PS? Line 7PS starts from point P, that is the center of this semicircle, and that's at point S, that is the point on the semicircle itself. So PS is the radius of the course circle that is equal to 8 units in its length. Likewise, what is the definition of line 7QS? Line 7QS starts from point Q, that is the center of this small circle, and that's at point S, that is the point on the small circle itself. So QS is the radius of the small circle that is equal to R. Okay, and PQ, what is the length of PQ? Actually, because of the fact that PSQ is one side line, it means that PQ is one side line. What is the length of PQ? The length of PQ must be equal to PS plus SQ. Again, PQ equals to PS plus SQ because PSQ is one side line. So PQ equals to PS, that is 8, plus SQ, that is R. So in total, the length of line 7PQ equals to 8 plus R. Okay, so in the next step, I copied this right rectangle PHQ in a new page and implemented the Pythagoras theorem on this right rectangle triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse, here, this is the right triangle PHQ. PHQ is the copied from the original drawing. The hypotenuse PQ equals to 8 plus R, PH equals to 8 plus R, and HQ is the missing side. So according to the Pythagoras theorem, PQ square equals to PH square plus HQ square. PQ square equals to PH square plus HQ square. So PQ is 8 minus 8 plus R, therefore HQ square is 8 plus R square. And it is equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ is the missing side, so we need the CTs. We open the brackets of this, both sides of this equation, equation 1, and find out that according to this equation, equation 1, 8 plus R square equals to 8 squared, that is 64, plus R square, plus 2 times 8, that is 16 times R, so it is plus 16R, this is equal to 8 minus R square. 8 minus R square equals to 8 squared, that is 64, plus R square, minus 2 times 8, it is minus 16 times R, so it is minus 16R, plus HQ square. Here we have 64 on both sides of this equation, equation 1, so 64 will get cancelled, and we have also R square on both sides of this equation, equation 1, so R square also will get cancelled. After cancelling those two expressions, we have only, in this side of the equation 1, we have only 16R, in the other side of this equation 1, we have only minus 16R, plus HQ square. So according to equation 1, we found out that 16R equals to minus 16R plus HQ square. Here we have the 16R to this equation 1, and we found out that 16r plus 16r is 32r, so 32r equals to HQ squared. Here we substitute 32 by 2 times 16, so in total according to equation 1, 32r is 16 times 2r, that is equal to HQ squared. Here we talk about out of this equation 1, and we found out that HQ equals to the square root of 16, that is 4, times square root of 2r. So in total HQ equals to 4 times square root of 2r. Here this side HQ equals to 4 times square root of 2r. But we already found out that quadrilateral HQMO is a rectangle, and we know that the opposite sides of rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side MO. But HQ is 4 times square root of 2r, therefore MO must be equal to 4 times square root of 2r. This small circle touches the big quarter circle at this point T. That is to say, those two circles have an internal notch between them at point T. And whenever we have two circles that have an internal notch between them, we can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the side line that connects their centers together passes through their touching point. So in the drawing we have the big circle, the center of the big circle is 0.0. And we also have this small circle, the center of this circle is 0.m. And those two circles touch each other internally at point P. That is to say, they have the internal notch between them at point P. Therefore, according to this rule 9, the straight line that connects their centers together is the straight line OM, must pass through point P. Or again, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing, because of the fact that the small circle touches the quarter circle at point T, they have an external notch between them at point T. Therefore, we can implement rule 9. The center of the big quarter circle is 0.0. The center of this small circle is 0.q. The straight line that connects the centers together is the straight line OQ. And according to rule 9, the straight line OQ must pass for point T, that is the touching point. Or OQT is one straight line. Again, the straight line OQ must pass through the touching point, that is point T, or OQT is one straight line. Again, according to rule 9, OQT is one straight line. If OQT is one straight line, it means that OT is also a straight line. But what is actually the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and that's at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. So OT is the radius of this quarter circle, that's equal to 16 units. And here OT equals to 16. What is the definition of line segment QT? Line segment QT starts from point Q, that is the center of the small circle, and that's at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. And because of the fact that according to rule 9, OQT is one straight line, it means that OQ must be equal to OT minus QT. Again, OQ must be equal to OT minus QT. Again, OQ equals to OT minus QT. So OQ equals to OT is 16, minus QT, that is R. So in total, we found out that the length of this line segment OQ equals to 16 also. In the next step, I copied this right blue triangle OQM in a new page, and we implemented the Pythagoras theorem on this right blue triangle OQM. Actually, this is the right blue triangle OQM that I copied from the original domain. The hypotenuse OQ equals to 16 also. QM equals to R, it is the radius of the small circle, that is equal to R. And we already found out that OM equals to 4 times square root of 2R. According to the Pythagoras theorem, in this right triangle OQM, OQ squared, that is the square of the hypotenuse, must be equal to QM squared plus OM squared. So OQ is 16 minus R, therefore OQ squared is 16 minus R squared, and it must be equal to QM squared. QM is R, therefore QM squared is R squared, plus OM squared. OM is 4 times square root of 2R, therefore OM squared is 4 times square root of 2R squared. So here we open the brackets on both sides of this equation and equation 2 and find out that according to this equation and equation 2, 16 minus r squared equals to 16 squared, that is 256, plus r squared minus 2 times 16, that is minus 32 times r, so it is minus 32r equals to r squared plus 4 times square root of 2r squared. 4 times 4 squared is 16, and square root of 2r squared equals to 2r, because the power cancels the root and we're left only with 2r. So in total, the value of this expression equals to 16 times 2r. So here we have r squared on both sides of this equation, equation 2. So r squared we get cancelled. After we cancelled r squared, on this side of this equation 2, we left only with 256 minus 32r, and it is equals to 16 times 2r is 32r. So according to equation 2, we can find out that 256 minus 32r equals to 32r. Here we added 32r to this equation, equation 2, and we found out that according to this equation, equation 2, 256 equals to 32r plus 32r is 64r. So according to equation 2, 256 equals to 64r. Here we divided this equation, equation 2 by 64, and we found out that r equals to 4 units. Because r equals to 256, that is 256 over 64, that is 4. So r equals to 4 units in itself. Repeat again, the answer to the question is that the radius of this small circle r equals to 4 units in its length. Okay, thank you very much.